Okay, here we are on a brand new video, and I represent that on the left hand side is a diagram that came out of a textbook. 1926 was first publishing, and it was mathematics for engineers, and the authors were Dull and Dull, Robert and Raymond Dull, and it was published by McGraw-Hill. And what I did was all I did was to program it to be interactive for intuitional purposes. So I said that it's interactive, so let's see what that looks like. Okay, the angle is changing, so it gives us an intuition about what happens with the quantities on the screen. Okay, I'm going to represent that the letter A represents a quantity that represents the measured distance between the center of this unit circle and this reference point right here, and that this A right here to the second power represents the measured distance between this center reference point and this green reference point. And I represent that the quantity A here is to the first power and the quantity A here is to the second power. So these symbolic values work in a very neat way. It not only serves as a label for a line segment, but at the same time it references the mathematical relationship between these two line segments. This is A to the first power, and this is the same value A, but to the second power. So that is a pretty neat thing about symbolic values. They can be used at the same time for their labeling value and for purposes of representing mathematical relationships between consecutive figures in the diagram. Okay, so over here we have a quantity B representing the measured line distance between this reference point and this reference point. So it's that quantity is B to the first power. Now here we see B again. That's the same exact quantity, but here it's to the second power. Now, as an aside, you notice this line segment looks shorter than this line segment over here. Now they're both consecutive powers of B, so why is this one shorter? Well, the reason is because this is the unit circle and all line segments in it are fractional numbers, so a fraction times a fraction is a product of two fractions is always shorter, always smaller. Okay, an example of that: 1/2 times 1/2 is 1/4. So this line segment better look shorter if this is to scale, and it is. This is supposed to be 1 inch. So I'm representing that if this was 1 inch, then this would be a fraction of an inch. So squaring that number, you should get a representation that obviously looks smaller than it, or in this case shorter, and it does. Okay, so I'm 3 minutes into this, and I'm going to jump over full screen to try to stay under 10 minutes. Okay, I've already drawn some things here, and the first thing that you see is I've got this triangle drawn here, and it looks like it's pretty busy, but it's actually the same diagram as in the interactive programmed representation on a previous screen. Here we see A to the first power, here we see A to the second power, the same way as it before. Here we see B to the first power and B to the second power. Sorry about that. And we see here, it's written here that this is the unit circle triangle. So this triangle is what I'm referring to as the triangle inscribed inside of the unit circle. So it too has all fractional sides, and that's the only way that this works. I've seen other people do this same experiment with similar triangles, which is, you'll see in a minute, that's what this is all based on. So as an aside, we have 3 triangles here the small one, the medium one, and then the largest one, and all three of them have the same angles. And the neat thing about when triangles all have the same, multiple triangles have the same angles, is that they also have a property called similar triangles have ratios of corresponding sides are equal. I've got that written right here, and you can pause the video and look up on Wikipedia, and you'll see that, and you can come back. It only take about a couple of minutes until you're familiar with that, until you're comfortable with that. If you don't already know about it, which most people looking at this are probably going to already know about it. Sorry about that. So on this lower left-hand side, right here, the ratio we're gonna look at the ratio of the adjacent over the hypotenuse, adjacent side of the triangle over the hypotenuse, for the large triangle and for the medium triangle. For the large triangle, adjacent over hypotenuse, let's look at that. Here's the large triangle, and the adjacent side is right here, and the hypotenuse is right here. So adjacent is A, and the hypotenuse is the identity element of 1. So we have the A over the identity element of 1 is the adjacent over hypotenuse for the large triangle. Now for the medium triangle, let's look and see what the adjacent to the hypotenuse is for the medium triangle. And that's going to be D over A. Okay, so let's look at that and see where we get that from. So for the medium-sized triangle, it's right here. This is our medium-sized triangle. And the adjacent side here is D. And the hypotenuse right here is A. So D over A. So when we multiply crosswise here, we get A times A, or A squared. So we have a squared term. And then here we have D times the identity element, which is just D. So these two being the same value, I can write A squared anywhere I see D. So that's the reason why when we have D, we can also represent that as A squared. Okay, moving on. Over here, we're going to look at the ratio opposite over hypotenuse for the large triangle and opposite over hypotenuse for the small triangle. Okay, so let's look at that. For the large triangle, it's B over 1. So let's look at that and see where we get that from. Okay, so we're looking for the for B over 1 for the large triangle. In other words, opposite over hypotenuse. So the opposite side of the large triangle is right here, and it's B. And the hypotenuse for the larger size triangle is right here, which is unity, or the identity element of 1, or C, the side C. So that's B over 1. Now, and you can pause your video if you need to be comfortable with that. And I apologize for that darkness there. I can't get away from it. The light's directly above me. So anyway, here we're looking for this. It's a small triangle. Opposite over hypotenuse for this small triangle. Here's the small triangle, and the opposite side's right here, which is E. And the hypotenuse is B. So E over B. Now when we cross multiply here, we get B times B. And when we multiply here, we get the identity element times E, which is E. Anyway, so this being equal to this, I can put B squared anywhere I see E. So up here, this is where E is. So it's also B squared. So here we see that A squared plus added to B squared is obviously equal to C, or since C is the identity element, then C times C is also C squared. So C and C squared, C equals 1, and C squared equals 1. So we can say C squared A squared plus B squared equals C squared only because C is equal to the identity element. Okay, so I think that's it, and I've got 10 minutes. That's really good for me. I've cut it down 8 minutes off of this last video. Anyway, please, if you like this, I've lost my cursor. If you like this, please like and please subscribe. Thank you very much. Oh, except I guess maybe I can have time to sort of summarize. What we've seen here is how this diagram, which was used in 1926 as a drafting aid, they quite literally drew this diagram to scale, and they used a protractor to set the angle accurately, and then they could just use a divider to be able to transfer an accurate value of A and an accurate value of A squared to another drawing. And they could accurately transfer a value of B and a value of the square of B to another diagram. Anyway, that's what they used it for. The first time I saw it, I thought it was a pretty neat relationship, where, in summary, the hypotenuse of 1 in a unit circle, or a unit, I'll call it a unit triangle, because it's inscribed inside of a unit circle, is broken into two parts. And the neat thing about it is that this part is a second power of this part, and that this part is a second power of this part. I just thought that was pretty neat and worthwhile sharing with everybody, and I'm hoping y'all think that's pretty neat too. Anyway, thank you, and please like and subscribe. Have a good day. Bye.